Do you still remember the happy times watching Tom and Jerry as a child? Those thrilling chase scenes. From the kitchen to the living room and then to the garden, every movement was so smooth and natural. Now, AI can also create such animations, and it's a full 1-minute complete story. Recently, a research team from NVIDIA, Stanford University, and other institutions, through a new method called test time training, has achieved a qualitative leap in AI video generation capabilities. Currently, the mainstream video generation APIs on the market, such as OpenAI's Sora, Meta's MovieGen, Luma's Ray 2, and Google's Veo 2, all limit the length of generated videos to between 820 seconds. There is an important technical reason behind this limitation. Traditional transformer models experience quadratic growth in computational cost when processing long sequences. Simply put, generating a 1-minute video requires not the equivalent computation of 23-second videos, totaling 60 seconds, but 11 times that amount. Let's use a concrete example to illustrate this problem. Suppose we want to generate a 1-minute Tom and Jerry cartoon, which includes multiple scenes. Tom chasing Jerry in the kitchen, then running to the living room, and finally chasing in the garden. If using a traditional transformer model, it needs to process information from all these scenes simultaneously, which would require enormous computational power. This is like asking a person to remember all the details of an entire movie at once. The difficulty can be imagined. The research team adopted a very ingenious approach, using test time training, TTT layers, to replace part of the transformer's self-attention mechanism. The key innovation here is that the TTT layer does not retrain the entire model at test time, but instead adjusts its hidden state through gradient updates at each step of video generation. This hidden state itself is a 2-layer MLP neural network, which has stronger expressive power than the matrix hidden state of traditional RNNs. To better understand how TTT works, let's look at the 3 main differences between it and traditional neural networks. First, in terms of training methods, traditional neural networks typically only update parameters during the training phase, while the TTT layer updates its hidden state at every step of video generation. This is like a student continuously learning during an exam. Traditional methods are like memorizing all the knowledge before the exam, while TTT constantly adjusts its understanding during the exam process. This dynamic adjustment capability allows the model to better adapt to complex relationships in long sequences. Secondly, in terms of structural design, the TTT layer uses a 2-layer MLP as the hidden state, instead of the simple matrix in traditional RNNs. This MLP contains twice the number of hidden units, enabling it to store and process more complex information. Imagine if the memory of a traditional RNN is like a simple table. Then the memory of TTT is like a smart notebook, which can not only record information, but also understand the relationships between information. When generating videos, the TTT layer remembers important information from previous scenes, such as Tom's movements, changes in facial expressions, and scene transitions. This information is stored in the hidden state of the neural network, rather than simply being compressed into a matrix. Third, in terms of computational efficiency, the TTT layer achieves linear complexity, rather than the quadratic complexity of transformer. It's like in a classroom. Transformer requires every student to communicate with all other students, while TTT only requires each student to communicate with the teacher. Specifically, the TTT layer does not need to compute attention weights between all positions like transformer, but instead adjusts the hidden states through gradient update tests to better predict future content. From a technical implementation perspective, the workflow of the TTT layer is as follows. First, it receives an input sequence, such as video frames or text descriptions. Then, it computes a self-supervised loss function, which measures its quality by comparing predictions of the current hidden state with the actually observed data. This is like a director filming a movie, constantly checking whether each shot meets expectations. This process repeats at each step of video generation, ensuring the model can continuously learn and adapt. The research team conducted experiments on the Tom and Jerry cartoon dataset, collecting approximately 7 hours of cartoon footage and adding manually annotated storyboards. During the training process, they used 256 Hone 100 GPUs, which took 50 hours. The final results showed that, in human evaluations, the TTT layer outperformed existing baseline methods such as Mamba 2 and gated DeltaNet by 34 ELO points. As a reference, GPT-4o outperforms GPT-4 Turbo 29 ELO points in the LMS's chatbot arena. However, this breakthrough also has some limitations. The researchers found that there are still some artifacts in the generated videos, which may be related to the limited capability of the pre-trained 5B model. In addition, there is still room for improvement in the current implementation efficiency. But this method opens up new possibilities for AI video generation, not only being able to handle longer videos, but also generating more complex stories. Each video is directly generated by the model, without editing, splicing, or post-processing. From cartoons and childhood memories to complete stories generated by AI today, we have witnessed how technology turns imagination into reality. The innovative technology of test-time training not only achieves a qualitative leap in AI video generation capabilities, but also opens up new possibilities in this field. With the continuous advancement of technology, perhaps in the near future, we will see more astonishing applications of AI video generation. Thank you all for watching. If you're interested in this topic, feel free to share your thoughts in the comments section. See you in the next video.